Hey everyone, and welcome back to ChemiVids. So last video we talked about engineering units and just classified a bunch of different engineering units into the SI system, into the American system, into other really commonly used units. And now we're going to talk about unit conversions. How do I get from one system to another? As it turns out, these are all figured out for you. So really all you have to become familiar with are tables like this. Just as a reference, I'm using the Elementary Principles of Chemical Processes book, and this is by Felder and Rousseau. It's a great resource for beginning chemical engineers. This is where this table came from. So as you can see, they have mass, length, volume, force, pressure, energy, power, all of those units that we talked about in the previous video, which I will link in this video. And they have all the different conversions between them. They even have some units we haven't talked about. And like I said, they're just units that you're going to have to become used to and become used to using. So let's do some practice here using this table. Let's start off with something simple, a length conversion, 13 feet to centimeters. So really the easiest way to do a problem like this is to write down what you have, 13 feet, and whatever starts up must come down. And that's so it can cancel, right? If I divide feet by feet, they both cancel. So we want to go feet to centimeters. And let's look on our chart and see if we have anything that will give us that direct conversion. So looking at length here, we can see that it has 1 foot is equal to 30.48 centimeters. So coming back here, we can say that 1 foot is equal to 30.48 centimeters. Multiplying that out, we can find out really easily that that is 396.24 centimeters. Continuing on, let's move to 200 gallons per minute to liters per second. So this one, again, we're going to write down what we have, 200 gallons per minute. And let's actually start with the denominator, this minute part. So like I said, what comes up must go down, but also what is down must come up. So we can say in 1 minute, right, this is down, now it's coming up, in 1 minute there are 60 seconds. And that's something I just expect you to know. That wasn't on our conversion sheet necessarily, but I think that's something we're all pretty comfortable with. And looking here, now we have to convert gallons into liters. That's our goal. So let's look at our conversion table for this. If I come back here, and we look at volume, I can see see how these are all equal to each other? Boom, boom. So I know that this and this are equal. They all have equal signs in between them. So I can say, this is where it gets tricky when the conversions get longer. 28.317 liters is the same as 7.4805 gallons. 7.4805 gallons. So the gallons now cancel, because what comes up must come down, and we're left with a liters per second of 12.6 liters per second. So continuing on, we have a density calculation. So this is moving from kilograms per meter cubed into grams per liter. Well, start with what we have, 1,000 kilograms per meter cubed. And now we need to convert kilograms to grams. So just a little tip, you can look in the conversion table and it has it right here under mass, kilograms to grams. But just something that will be useful to you is kilo in the SI system really means 10 to the third. And the base that it's based off of is grams. So if I have a kilogram, I have 10 to the third grams, or 1,000 grams. So coming back here, I can just say right off the bat that 1 kilogram is equal to 1,000 grams. So now let's convert this. We got our kilograms out of the way, so now let's convert our meters cubed to liters. So I think we're going to need a conversion table for this one. You can see that under the volume section, let me change pen colors here. Under the volume section, we have 1 meter cubed is equal to 1,000 liters. That's something you may just want to memorize. It's very, very common. So we can come back here and say that 1 meter cubed is 1,000 liters. Now, before you pull out your calculator, normally what we would do is we would just say, okay, I'm going to multiply across the top like this, right, and get an answer on the top. Multiply across the bottom like this, get an answer, and then divide the two. Let's be a little smarter than that. Instead of that, let's go ahead and look at our numbers. I have 1,000 divided by 1,000 here. And so as it turns out, 1,000 kilograms per meter cubed is the same as 1,000 grams per liter. Pretty cool about density. So if you ever see these two density units, know that they're interchangeable. All right, so now we're getting a little harder. We're talking about force now. So we have 30 pounds force to newtons. Well, I remember there was a force section on this, so let's go to the force section. 1 pound force is equal to, oh, look at that, 4.4482 newtons. So coming down here, we can say 30 pounds force, and 1 pound force was equal to and I've already forgotten it, 4.4482, 4482 newtons. Doing that math out will get us to 133.446 to be exact newtons. Now, I'm writing out the full decimal versions of this. Beware of significant figures if your professor really harps on that. I'm just writing as far as we can go on decimals. All right, continuing on. Now we have a little tricky thing here. Let's say I go into my bedroom, and on my scale, I weigh a package and it weighs 30 pounds. That is actually 30 pounds force, technically. Because if I were to take that same scale and go onto the moon, it would weigh less, because gravity is less. So we're going to try to figure out how many pounds mass that is on the Earth. Okay? So looking here, first of all, how do we relate force and mass? Well, back to the other video, it is a mass times an acceleration. Well, in this case, it's an acceleration due to the gravity on Earth, so we can replace this with the gravitational constant. Coming into here, we can say, all right, 30 pounds force is equal to some amount of mass that I don't know, and I give you a hint up here, that G is equal to 32.174 feet per second squared. Uh-oh, we've run into a problem. Because to solve this equation, I would divide this over, right? So I would get 30 divided by 32.174 feet per second squared pound force. And you know what? So it doesn't look like mass to me, but let's check and look. Lo and behold, we have a conversion that gets us from those funky units into something we can deal with. So 1 pound force is equal to 32.174 pound mass times feet per second squared. So coming back down here, we can say, all right, I know that 1 pound force is equal to 32.174 pound mass per foot second squared. And that should be equal to our mass, right? Well, if we cancel units, so foot per second squared, pound force, oh wait, this is the same number too. Turns out our mass is actually 30 pounds mass. Now, this is only true on Earth. The acceleration due to gravity is different on different planets and things. So, I'll go ahead and let you work out the kilogram version of this. The two ways you can do this problem are you can convert the pounds force to newtons, use F equals mg, and calculate a mass in kilograms, or you can go through the same process that we just did, so pounds force to pounds mass using F equals mg, and then convert that to kilograms. Why don't you try it both ways? Here, go ahead and pause the video and try it, and then see if you can get the right answer. Okay, so the answer should be 13.6 kilograms.